Hi, today we continue to the third lecture about condensation in deep learning. So while we study condensation, one of the motivation is originated from the study of phase diagram. We want to study how hyperparameters affect the training. Specifically, we focus on initialization. Let's take an example of water. The first diagram of water can give us a lot of information. For example, once we know the pressure and temperature, we can know which state the water is in, such as in solid state or liquid state or gas state. And once we know which state the water is in, we can know a lot of properties about this matter, such as the density and viscosity and so on. For neural networks, can we also find similar quantities that can determine the neural network's behavior? Let's get started with two-layer neural networks. We consider these two-layer neural networks, and this is the inner product of the input with weight W. And in this form, actually, we can also expand this to weight and bias form by this expansion. There is an alpha here. This alpha is a constant. We include this constant so we can study different forms in the literatures. To train this neural network, we need to initialize these trainable parameters A and W. Usually, we can initialize these parameters by Gaussian distribution or uniform distribution. And what we care most is the scale of this initialization. For Gaussian distribution, we initialize with zero mean Gaussian distribution, and for A and W, we use different variance. And usually, the scales for alpha, A, and W, we usually use the form m to power minus lambda. For example, alpha, beta 1, and beta 2 can be used with different scales. And in this form, we can see the usual initialization method in theory or in practice. And we can see always that this lambda is usually equals to either 0 or 0.5. Now we want to study how initialization affects the training result. Here's an example. If we use large initialization, medium initialization, or small initialization, and we want to check how the result varies across these different initialization. The training data are 4 points, and we use the same training data for different initialization. And we can see the neural network after training are very different. In the first case, large initialization, we can see the curve is not smooth, but with some turbulence. And for medium initialization, it's very smooth. And for small initialization, is very sharp in the transition. And note that we use ReLU as activation function. The ReLU here is a very common used activation function that if x is larger than 0, is a linear function. And if x is smaller than 0, is a constant 0. And we can see that the key point, the key thing for the ReLU activation function is the turning point. Because of this turning point, so this function is nonlinear, so we can have ability to fit almost any function. Otherwise, you can only fit linear function if the activation function is linear. And the turning point, the position of turning point is very important. Where is the turning point? That is Wx plus b equals to 0. That is x equals to minus b over w. That is the turning point. Now we can take a look for this small initialization after training. For so many neurons, actually, there are only two turnings, means that the activation functions, many activation functions, their turning points are overlap. And for this median result, if we want to get this very smooth transition, there must be many turnings, but definitely they are not random. They are learned. They are very, very carefully optimized after training. And for the large initialization, there are also many turnings, so it can has many turbulent. And these turnings seems still random, just like initialization. And the key thing in this talk, in this lecture, is we found that for small initialization, there are many neurons will behave very similarly. And the same conclusion is the condensation phenomenon we found in the experiment and also supported by some theoretical study. Initially, the neural network's parameters are randomly initialized. They are very different, but after training, seems neurons in the same layer will get clustered. For example, in this very simple toy example, the first two neurons get clustered, and the last three neurons also get clustered. That means their input weight are exactly the same for the first two neurons and also for the last three neurons. If this condensation happens, the original 5 neural networks will be effectively equal to a network of only 2 neurons. So we have mentioned about these long-standing problems proposed by Leo Bremen. Why don't heavily parameterized neural network overfit the data? Now we can provide answer to this question. So for the model or network, if the number of parameters is larger than the number of samples, for the same training data, we can often have multiple solutions. And after training, since the neural network can always pick a good solution. However, for the loss function, these different solutions, there are no difference. For the loss function, they're all equal to 0. So the key question we have mentioned is, what is the implicit bias of neural networks during the training? That is the question we want to ask. So we have mentioned about the frequency principle and also this condensation. They are simple but with rigorous theoretical analysis and can inspire efficient algorithms and can explain the overall parameterization puzzle. How? So usually traditional theory tells us for models with much larger parameters than the samples number, it can easily overfit with this fluctuated curve. However, for neural network, due to this low frequency bias and also due to this condensation, it has small effective neural number, so it can bias towards this simple smooth function. That is a very simple glimpse of the condensation we are going to talk about. And in the following, we want to ask a very key question: what quantities to differentiate different regimes? That is, one, the neural network can have this condensation, and one, neural networks do not have this condensation, and otherwise it has linear property. And if we scale up the model to large model, how to initialize the neural network to keep its behavior similar. And if we have different combination of these initializations, are they similar or different? Those are the questions we are going to answer in this lecture. So we now continue to study the regimes in a more quantitative way. For example, for some questions, if we want to keep the neural network in a similar dynamic behavior, such in linear regime or condensation regime, when a network width scale up to a large width or large model, how should we change different hyperparameters, such as alpha, beta 1, and beta 2? And another question, as we have seen, this alpha, beta 1, and beta 2, they could be very different. And what is the effect of their combination? If we have two combinations of these hyperparameters, how can we determine if they are in the same dynamic regime or not? So to answer these questions, we need to find what the quantities that can differentiate the dynamical regimes. The model we study is still two-layer neural networks with ReLU activation function. For such neural network, the only nonlinearity comes from the nonlinear activation functions. And the weight that inside this nonlinear activation function is the only one that can affect the nonlinearities. So we will focus on study how this parameter can affect the nonlinearity. Let's go back to the first example we have seen that for different initialization scales, the neural network will use different functions to interpolate the same training data. For large-scale initialization, there are still many tunings for activation function. And for very small initializations, their tunings of activation function will have a significantly change during the training. And for these 4 training data points, there will be only 2 turning points. And what will determine these turning points? By the definition of activation function, the turning is determined by Wx plus b equals to 0. So the turning is at this minus b over W. So W in the nonlinear activation function can significantly affect the turnings for this ReLU neural network. So we will focus on the evolution of how this input weight evolve during the training. Yeah, we still abuse the notations here. The input weight and bias are explicitly right out here. And we can, for one-dimensional input, we can write this W and B in a two-dimensional coordinates. And we will focus on 2 quantities. One is the angle, the orientation of this input weight. And the other is the amplitude of this input weight to study how much contribution this neural network have for the final output. And this orientation we have mentioned actually is quite important because of this B over W. For this ReLU activation function, the 0 point is determined by this x equals to minus to b over w. So for each angle, each orientation, it will determine a turning point. And as we have seen that the turning point is quite important. So now let's take a look at the previous 3 examples. For these 3 examples, gamma here indicates the initialization scale, and gamma small means large scale, and gamma large means small scale. And let's take a look at this first example here. Each dot actually indicates one neuron. So, for example, A1 or W1 hat can be plotted here. And this A1 indicates the amplitude, and this W hat indicates the orientation. So we can use number from -pi to pi to indicate this orientation. And since we have many neurons, so we can have a lot of dots here. And there are two colors. For the cyan color, it indicates the feature distribution of initialization. And for the red color, it indicates the feature distribution after training. And for larger scale initialization or linear regime, we can see the feature distribution does not change so much during the training. That's why we can perform the first order Taylor expansion to approximate the final trained network parameters. And that's why it's called a linear regime. And since all these angles are almost determined by the initialization, so we can see a lot of small fluctuation in the final output. And now let's take a look at another extreme case. We call it condensation and try to understand why condensation is named for this regime. So we normalize the amplitude. So the initial feature distribution are so small, we barely see it. But we know that they are quite different between the initial distribution and the final distribution indicated by the red color. After trained, there are still many neurons they are active, meaning they have a significant contribution to the final output, but their orientation are exactly the same. So they will have the same turning point position. And as an aggregation effect, the final output will only have two turning points, and that can fit this full training data still very well. And why we call it a condensed regime? Because the orientation of neurons, they are condensed in only two isolated directions. And that is the reason we call it condensation. So we know that for small initialization, the neural network will tend to condensation. For large initialization, the neural network will tend to linear. And how small is small and how large is large? That is the key question we want to answer in the following slides. So to answer how small is small and how large is large initialization, we will start from the two-layer neural network and gradient flow, and to study the phase diagram to differentiate linear and nonlinear regime. For neural network, we consider loss function in this mean squared error form, and consider the gradient flow, that is the gradient descent with limit of small learning rate. And the initialization is theta 0, and that is the key for our study. The model we have introduced, that is the model of two-layer neural network with a prefactor 1 over alpha here. And the output weight is initialized with Gaussian distribution and scaling beta 1. And input weight is with scaling beta 2. And we also have slight abuse of notation here to combine the bias term into input weight. And to study the evolution of the weight A and W here, we encounter difficulty to compare the different training trajectory. That is, they have different scaling. So to compare the different training trajectory, we can normalize the weights by their scalings. So we study another normalized weight A bar here is the A over is scaling beta 1, and so is W bar is the W over beta 2. And we want differentiate this normalized or non-normalized weight because we only consider the normalized thing. So the gradient flow from the normalized weight can also be derived through the gradient flow of the original parameter. And also from the input and output weight, we can also have this gradient flow. And now let's take a very carefully observation on these two gradient flows. We can see that there are some coefficients here are very important, and note that the evolution time is also scaled, but we only care about the final result. We don't care about how much time we train the neural network. So the scaling of timing, evolution timing, is not important. There are two very important factors here. That is beta 1 times beta 2 over alpha. And the other is the ratio of beta 1 and beta 2. And now let's take a look on these two coefficients, but not into the details of the gradient flow, because they are so important for now. So what's the meaning of this kappa and kappa prime? Kappa actually indicates the scaling of the neural network output in the initialization, because alpha 1 over alpha and also beta 1 and beta 2, their product indicates the initial output. And kappa prime means the difference of the initialization of A and W. Why is important? Now let's take a look. If we have gradient of with respect to this A, we will have this W. So the amplitude, the scale of W, will affect the learning speed of A. And if we have gradient for this W, we have this A in the other gradient. So the scale of A will affect the learning speed of W here. So this beta 1 over beta 2, actually, they will determine the learning speed difference for these two parameters. So here is beta 2 minus over beta 1, and this is beta 1 over beta 2. Why their learning speed are so important, or their difference is important? Because they will affect the neural network in different ways. For this AK, the network is always linear with this output weight, but it's nonlinear with WK. So if the network after the training A has significant change, it's not so important because it's linear. But for WK, it's nonlinear. So we need to more focus on the change of WK. So kappa, the kappa here indicates the initial output. If the initial output scaling is large, it can fit the neural network. Its scale is similar to the target function. Then the change for the total output is also not so large. Like, for example, now order 1. Then you only need to have order 1 change. And you have M neurons. Once this change is averaged by all neurons, and in the infinite width limit, the change of each neuron will go to 0, so the change is very small. And if the change is very small, it will stay in linear regime. And since we have mentioned that these alpha, beta are all have the form or power of the network width, and in the infinite width limit, we can study their power only, this gamma and this gamma prime. So why we study this infinite width limit? Because, for example, in the phase diagram study of water, if we want to have a sharp phase transition, we need to have this thermodynamic limit. The particle number should go to infinity. And then we can identify the pressure and temperature as the effective coordinates for the phase diagram, because they're effective independent and they have dynamical similarity. If you have the same pressure and temperature, then the state are similar. And it can have this differentiation differentiation capability. If they are different, their dynamic state will also have different. And we will show that this gamma and gamma prime, they can also serve as a function similar to this pressure and temperature. One is the initial scale, the other is the different scale of input and output weight. By this gamma and gamma prime, we can write out all the for the common initialization method and also theoretical study the initialization method. We can write it down, and we can see that for lect3 and her initialization, they are similar because we have this infinite with limit. And now, based on these tools, we can study the linear and nonlinear regimes. So what is linear? Actually, the linear means the network can be effectively approximated by the first order Taylor expansion. This is the gradient of network with respect to the initial parameters, and that is the difference of the trained network parameter with respect to the initial parameter. Suppose the initial output is equals to 0, we can achieve this by some trick. And the key thing we want to study is the relative distance of the input weight during the training. That will determine the networks stays in the linear regime or stays in the nonlinear regime. And when we have this infinite width limit in a linear regime, this relative distance will goes to 0. And in a condensed regime, this relative distance will goes to infinite. And there is a critical regime that this distance stays in order 1. Here's an example for our study of these two-layer neural networks. We let gamma prime equals to 0, meaning beta 1 and beta 2 they have the same scale. And we only change this gamma indicates the initial scale of the network output. And since there is a negative sign here, so if you have small gamma indicates large initialization. And we run several experiments for different network width and compute the relative distance. And we can see for this scaling, as the network width increase, the relative distance will decrease. So as we can guess that as the network width goes to infinity, this relative distance will go to 0. So this will stay in the linear regime. And for the critical regime, gamma equals to 1, as the network change, the relative distance of this input weight always stays very similarly. It's independent of the network width. And for the condensed regime, gamma is very large, initialization scale is small. The relative change will increase as the network width increase. So this definitely will be in the nonlinear regime. And so we can see that to determine that is in the linear or nonlinear regime, we can only study the slope of this tendency. For the linear regime, as the m increase, it decrease, so the slope is negative. But for the condensed regime, its slope is positive, so the change will also goes to infinite. So we can define this slope for studying their linearity. And we can see here in these experiments, we have different combination of alpha, beta 1, and beta 2. But for each point, they have the same gamma. And we also keep gamma prime equal to 0. So we can see that for different combination, if their gamma equals to the same, they have the same slope. So meaning we identify the hyperparameters or the factors, the quantities we identify, they are effectively similar. If they have the same value, then the dynamic are effective similar. Now we can run more scheme for hyperparameters gamma and gamma prime. For the synthetic data, 4 data points we have used for training data. In this red regime indicates the slope are negative, meaning they are in a linear regime. But for this blue regime, they are in a nonlinear regime because the slope are positive. So the relative change of input weight will also goes to infinity. And similarly, for this data set for two-layer neural networks, we have a similar picture. And the dashed curve means the theoretical guess or theoretical study to reveal their separation. And the star points is the interpretation of our experiments. So the experiments and theory are quite consistent. To be more specifically, we can have a rigorous study to show that in this regime, the relative distance will go to zero as the network width goes to infinity. And for the other regime, it will go to infinity. So it will be very nonlinear. And we can also see that for like Xavier, near field, and decay, they are all in different points of this phase diagram. And for three-layer reduced neural network, there are 2 hidden layers. And for this regime, they are all linear. But for this regime, for the first hidden layer is in a linear regime, but for the second hidden layer is in a condensed regime. So different layers can stay in different regimes. And also, you can plot different initialization method in this first diagram. People might care about this. Do we use neural network in linear regime, such as Xavier or Zhi-Qin initialization? They are all in a linear regime. But actually, the answer is not or yes. This first diagram is only for infinite width network. And for finite width network, there is nonlinearity, but not too strong, even for this initialization method that are not far from the separation of regimes. So up to here, we have identified linear and nonlinear regimes empirically and also theoretically for 2 and 3-layer reduced neural networks, and show that there is nonlinear regime and also linear regime and also critical regimes. And the next that we will show in nonlinear regimes, condensation phenomenon is very common. Now we are going to talk about condensed regime. So in condensed regime, this condensation phenomenon is very common, and we have mentioned about this. A neural network is initialized randomly but with very small scale. After training, neurons in the same layer will get clustered. And in this toy example, the first 2 neurons will have the same weights, and the last 3 neurons will have the same weights. And this neural network of 5 neurons will be equivalent to a network of only 2 neurons. So the effective number is much larger than the superficial number. That means this over-parameterization neural networks actually is low complexity. And we will study the training process of this condensation. And we use an example of 2-layer neural network to fit one-dimensional data. And those blue data points are the training data points. And we will study this 2-layer neural network. The input will have this 2-layer, have this linear transformation, and then go through an activation function, and then go through another weighted summation. And this is the loss function during the training. People might wonder that we usually don't have this flat curve, flat region during the training. Why you have this one? The reason is also simple, because we use very small initialization, much smaller than the usual used initialization for theoretical study. To make this phenomenon more clear, So we pick several points during the training to see the weight distribution. Here, and for each point here is one neuron, meaning one index J. For example, here maybe W1 and B1. And the x-axis is the value of input weight, and the y is the bias. And this movie actually shows during the training how these weights will evolve. Now let's take some snapshot. So in the epoch 100, many neurons are still stay at their initial point. But some neurons will have very significant deviation from this initialization. And similarly, each point here indicates one neuron, and its x value is W, and its y value is the bias B. And we can see that those neurons who has large deviations, they have some similarity. That means they are in the same direction in this two-dimensional plot. And in a 100 epoch, there is only one direction emerge from the training. They are not random. They have some very specific direction for those who grows up. But we know that if we only have one turning point for this ReLU activation function, it can never be able to fit a curve with many turning points. We have mentioned in the first piece of this lecture. So the neural network will have another direction emerge during the training. And similarly, there are not only one neuron, but a set of neurons that grows up, and they are in the same direction. But two turning points are still not able to fit the data. So after training, the neural network continues to grow more and more directions. This is the 3000th epoch. And after training in the final epoch, we can see that there are 5 directions emerge to fit the data. So another very key important feature of this condensation is the complexity of neural network increasingly grows during the training. The number of directions neurons condensed at gradually increase during the training. This is very important if we want to use the least complexity to fit the data. How should we do? We should test. Just increase the complexity one by one until we can fit the data. So we can use the least complexity to fit the data. And we know the less complexity the model is, the better chance the model can have good generalization. We might ask, what kind of initialization leads to this condensation? Or in another case, we call it a linearity. It doesn't have this difference of so much change of weights. And we found that this is the first diagram we have shown for two-layered ReLU neural networks. This blue regime is the linear regime, meaning if the neural number goes to infinity, after training, the weights after training deviate very small from the initialization. But for this green area, the weights will have significant deviation from the initialization. And we found that in this regime, there is always has condensation formula. So here's an example. So the x-axis number here is the gamma of our initialization scale, and this y-axis gamma prime indicates the difference of the input weight and output weight. And this is the linear regime, and this is the nonlinear regime. So what's the different number, different color here? The different color indicates the yellow color is the network of 1 million neural number, and the red color is the neural network with only 100,000 neuron. And for the blue one is for the network with only 1,000. So we can see that as the number of neurons increase, this condensation is more significant. This is also the x-axis for this small picture is also the orientation, and the y-axis is the amplitude, and each point is 1 neuron. So we can see for this condensation regime, there is always condense happens during the training. And for three-layer reduced neural networks, we actually have a similarly phenomenon that for nonlinear regime, although more complicated, it always has condensation formula. And for practical nets, we want to ask if this condensation still happens, because for practical nets, the initialization is not so small. So here's an example of a pre-trained raster net 18, and we download its weights and to examine if there is condensation happens. So we regard each kernel as a unit, and for each kernel we have its convolution weights, and we plot these weights into a vector, and then we compute the cosine similarity between each pair of kernels. So this is the initialization. This index and the neural index or kernel index. And we can see in the initialization, there is no significant clustered group, meaning the direction of different kernels are quite different. But after training, we can see some neurons, some kernels, they are clustered. So in a coarse-grained sense, it's about like two large groups here. Meaning there are many kernels that are very, very similar. So in this piece, we actually shows that during the training, the kernels will gradually condense, or the neurons will gradually condense, and we can also see that it's very common in nonlinear regime, and also in practical nets, there is also condensation. And in the next piece, we will study why condensation can happen. Now we continue to study why this condensation can happen. Actually, this is a very complicated, a very difficult question to answer. And we will not give a satisfied answer. We only provide some study or understanding in the initial training process. So now we review the neural network we use. It's a two-layer neural network. And this W can be extended as the input weight and also bias term. And this X can also extend it as the input and also a constant one. And similarly. So we have this loss function used by this mean squared error, and this is the network output, and this is the target function. And we train the neural network by gradient descent with the learning rate goes to zero limit, then we get this gradient flow. And for initialization, we use very small initialization. This W is a very small scale number. So once it's product with this input is also a small scale number. And then we can write out the gradient flow for each parameters for A and W. The very interesting thing is we can look more carefully into this network structure. So we know that the neurons, they are summed together to have this final output. So we know that neurons, they have the equivalent position in this network structure. Once we write out the gradient flow for W1, we definitely can write out the gradient flow for the W2 immediately, because all we need is to switch the index of these two neurons. So finally, actually, we can write out the gradient flow for input weight with a uniform ODE system. And once we inject the AJ and WJ values into this A and W, we should be able to get the gradient of this J's neuron. So all neurons, their input will follow this ODE system. So actually, we can write out or we can plot the field, the gradient field of this input weight. That is, once we have this specific W and A value, we can obtain this gradient. So we can write it out. This is W and this is B. And this is the gradient field, meaning for this here has values here, and its gradient is towards this direction. And at the initialization, we can see all neurons, they are all around the 0 point because we have very small initialization. And after training, we can see they evolve towards some specific direction. Why? Because in this field, there are 4 directions that are stable, meaning once neurons goes into this direction, then their direction only change. It will stay the same. Because we use very small initialization, very close this initialization scale, so the field is very simple. And that is the reason why neurons will get clustered or they have the same direction, because they follow the same direction, the same gradient field, the same ODE system. So they will evolve towards the same stable point. And for more complex activation function, network structure, such as convolution and gradient flow training, we can always obtain this similar result. The key thing is these neurons, they have the similar or they have equivalent position in the network structure, and that is the key. And we can further estimate the training time for initial condensation for smooth activation function. Similarly to ReLU activation function, if we study the activation function such as TENCH, we can have similar phase diagram, and we can estimate in different regime. In regime here or in a regime in the downside or upside, they have different initial condensation time. So for this linear regime, we can prove that neurons won't get clustered or won't condensed in a linear regime. But for condensed regime, we can prove they will condense initially at some training time. And we will show that in this regime and in this regime, their estimation condensed time is very different because their training behavior leads to nonlinearity is very different. In this orange regime, the evolution of W is slower than A, and in this regime, A is evolved slower. And in this regime, T is proportional to log M. M is the network width. And in this regime, T has a function, power law function with respect to the network width. And we can prove this for this double-leg regime. This is the log M. This is the condensation we observed during the training, the initial condense. They are in a very clear linear relation for different initialization. For another regime, A-leg regime, this is log T, this is log M. They also have this linear relation, so we can prove that this theoretical study can support the initial condensation. And in next piece, we definitely we actually wonder that if after condensation, the neural network is equivalent to a small network, why we don't train a small net, but train a condensed large network. This will be related to embedding principle we are going to talk. So in this piece, we will talk about this embedding principle try to answer. Definitely, we cannot answer this question completely. Why not train a neural network smaller, but not a large condensed one? Consider this, we have limited computing resource. If we train a very large one, it seems we will waste a lot of computation resource. So we are mentioning this, although we use a very large neural network to fit these 4 data points, but actually after training, there are only 2 effective neurons. That is, this ReLU and this ReLU, their summation is enough to fit these 4 data points. And the question is, the original large network and the 2 smaller effective network of only 2 neurons, are they similar? If so, why don't we just train a small network? To study this question, we also perform a series of experiments. We use networks to fit the same data but with different network width. And now we put all their loss function together and to see their similarity and their difference. Now let's take a look. The training data we use is the blue star points shown here. And we use a network with different widths, and they are completely independent training, but with the same initialization scale. The same gamma prime is the same in our phase diagram, so they have the similar training behavior. So this curve, they shows the loss function of different networks, but they have very, very much similarities. They have this plateau and the same loss position. So here's an example. We pick this plateau out and plot the output of networks at this loss. And they are shown here. They are quite similar, right? And we can also plot their condensation. They are also very similar. This is an orientation, this is the amplitude, and they are very similar. And in this plateau, meaning these gradients are very small, right? If gradients are very small, in the limit case, 0 gradient, that is the critical point. So they are very similarly, have very similar critical points. And because the networks can escape these critical points, so highly possibly these are saddle points. So neurons will have neural network of different widths that have similar saddles, similar loss, similar output, and similar cadence. That is what we observe from these experiments of a lot of loss functions during the training. But this is only one-time experiment. So to see some more stable conclusion, we perform multiple experiments. And we can plot a loss spectrum. That is the distribution over multiple trials of training. So for a network with M neurons, so we fix the initialization and we train it multiple times. And now we count the frequency of all loss functions in a small interval. For example, if the loss function is, we consider the interval within this very small interval around this -2. Okay, and we count, for example, in this here, and we count how many epochs, for example, for this red curve, and we consider this red curve. Let me use a curve. Okay, we consider this small interval. Okay, small interval. And then we count how many training epochs within this loss interval. And we have multiple time of training, so we can sum all the interval all the epochs number, and we can get the final number, and we indicate it by some color. So for this interval, there are very few epochs, so this color may be very small, very dark. But for some other place, like here, some other place like here, this one and this one. So there's a plateau here, right? There's a plateau here, so there are many epochs. There are many epochs that this color is very bright. So in this counting the frequency, we can get a spectrum for the loss function. So if there is a color, very bright color here, meanings in this loss function, in this loss value, there may be plateau here. Like here, there's a plateau. There's a plateau in this loss value. And now we can combine the all networks together, and we can get this complete loss spectrum. So we know that there's a bright curve around here for all the networks, meanings they will have similar plateau here. But for smaller networks, this is more bright. But for large networks, this is less bright, meanings the large networks stay at this loss value with fewer training epochs, meanings they can escape this loss value much easier compared with this smaller width network. And there is a tendency here, meanings large network, they tend to have this plateau at a smaller loss value, meanings larger network easier to decay loss function. So although they are very similar, in some sense they are similar, but they have difference. The difference is for large network, it seems easier for training because it can easily go to smaller loss, or it can easier escape the critical points. So we can study the similarity and difference of different width network from the loss landscape, and we found a very key property of network loss function that is called embedding principle. It says the loss landscape of any network contains all critical points of all nano networks. Now consider this network from information propagated from L-1 layer to L layer to L+1 layer. And we pick a neuron in the L layer and split it into two neurons. But this split has some very strict rules. It has the same input weight. The input weight is copied. And the output weight is split with a fixed ratio. So for this neuron, in the previous structure, it received a full output from this black neuron, but now it receives alpha percent and 1 minus alpha percent from these two neurons respectively. But their summation are the same compared to this original network. So it's easy to get this. The output of the nano neural network and the white neural network, they should be the same. And one step further, we prove this. If this nano neural network is at a critical point, and you can also have this white neural network at a critical point, meaning if its gradient is 0, this gradient is also 0. So this copy indicates we split this network in a way of condensation. And by this embedding principle, we can study the properties, and we show that larger networks, it will have larger degeneracy. Degeneracy means the eigenvalue of Zhi-Qin has more zero eigenvalues, meaning its volume is larger in some sense, so it's easier to attract the training trajectory. And for large networks, it almost always have more descendant direction. It always have more descendant direction, meaning it's easier. It has more direction to escape. It's easier to decay the loss. And we can also prove this in some experiment for synthetic 4-point data fitting problem. We first use a 2 neuron network to fit it. And after training, the loss is not so small, but it cannot decrease anymore. And the Hessian matrix, the eigenvalues are all larger than 0, meaning it's local minimum or global minimum. And now we don't train this network anymore. We just split it into a larger width network by embedding principle, this embedding operator. And we can see that there is one negative Hessian eigenvalue emerge, and also a 0 eigenvalue emerge, meaning there is one descendant direction. So it's not a local minimum anymore, it's saddle point. You have chance to escape, and its volume is larger. And once we embed it into a large network, more descendant direction emerge, and more 0 eigenvalue emerge. Similarly in other data points. So we may comment in this way, maybe why larger? Maybe this is the reason why we observe that, why we use wider network. Why wider network is easier for training? Because it's not local minimum anymore. It has more descendant direction. So although the gradient descent somehow cannot guarantee you to find a global minimum in a non-convex problem, but the neural network loss landscape has a very, very specific structure to help you to obtain this global minimum, and in a very specific way that is condensed into more and more neurons. So we will use a cartoon to intuitively understand. So we have these initial parameters, and we want to finally achieve this good global optimization point. And this path is very rough, but don't worry. The first neurons global minimum or critical point will guide you to achieve in the first station. In this station, the networks expressed as a simple function, but it's not enough to fit your data points. So you go to another second station, that is a network of two neurons critical point. And the complexity slightly increase and the loss decrease. And this is also a critical point, and you will attract your training trajectory just like a policeman to guide you to go. And then follow this guidance, you can get to these three neural networks, critical point, and fourth and fifth, and finally obtain the network that can fit your training data. And the network has almost the smallest complexity compares with this superficial complexity is very small, and that is due to the condensation. And since in the condensation case, neurons actually can be equivalent to few neurons, so we can do this pruning. Here's an example, a very tall example. We use 400 neuron with network 2-layer to fit these missed data points. And this is the training loss because we use smaller, very small initialization scale, so there is some plateau here. And we take out this point, and we examine the cosine similarity of the input weights of different neurons. And we can see that many neurons that have shown these large similarities for their input weights. So we can combine these neurons into one. So finally, we compress these 400 neurons into 58 neurons. And then we train it after this pruning, or we just simply sum their output weight together and replace the one by one neuron. We can see that it quickly goes to another settle point, and this loss value is exactly the same as the one we pick from the originally large network. They are the same. And we can see at this point, the network output actually is exactly the same between this reduced network and the original large network. On the original network, this column indicates the samples predicted as 0 by the original network. And this Y value here indicates in these samples the prediction of the reduced network. This color indicates the number, and we can see that all samples are concentrated on this diagonal. Indicates the original network prediction and the reduced network prediction are exactly the same. And now these colors are different because the samples that the neural network predict as each category are different. So there is some difference in the colors, but we can see that they are all concentrated on this diagonal, meanings the reduced one and the original one is the same. So we put this technique to a problem we are doing in using the neural network to replace the chemical reaction in the turbulent simulation. This is the original result, and this is the network. The network replaced the chemical reaction computation, and they are very similar. And now we reduce this network by the previous technique, get a smaller network width, and then the results are also very, very similar, meaning this technique is effective. So in this piece, we show that through experiments, we found that larger networks, it seems easier for training. That is the reason because of this, due to this embedding principle, there will be more descent direction once the network is embedded into a larger network. And this embedding principle is very universal, is independent with a lot of factors such as the network width, the loss function, the training data. So it's a very intrinsic property of neural network. And in the next step, we will go into more details of this loss function. This is the last piece of condensation. We try to get back to our key question about generalization. What condensation benefits in generalization? This is a very old problem about the generalization. If we want to have exact recovery of a target function, how many number of sample should we have? Traditionally, if you have n parameters, we usually will have m samples. This is the worst case estimation because we need one sample to have one condition for one parameters. For example, for Nyquist-Shannon sampling theorem, for target function with max frequency f, we usually have 2f Fourier basis. So we need to have at least 2f uniform samples. And for linear regression or polynomial fitting, we should have m samples for m parameters. But for nonlinear model such as neural network, we found that this doesn't hold because we seems can recover at a over-parameterization case. Even the number of samples is much smaller than the number of parameters. We still have chance to recover this target function or get very small generalization error. So in previous or in traditional study, we usually use complexity to study the generalization error, such as radiometric complexity. This radiometric complexity can be used to bound the difference between training loss and also the generalization loss. So if you have a model with very small complexity and can also fit in the data, then the difference is very small. The training error usually small, so the test error is also small. But however, for neural network, we usually don't. We usually find this doesn't work because the complexity is very large, and this is the worst case estimation. So the bound is also meaningless. It doesn't give any guidance for our practical training. Here's an example we have shown previously that even you use a very large network, more than 1 million parameters to fit a data set of just 60,000 data points, it can not only achieve good training error, but also very good generalization error. The question we ask is there really so many effective neurons in these large networks? We have shown that actually now, for this very simple case, although we use like 100 or 1000 neurons to fit these 4 data points, and after training, there are actually only 2 effective neurons remained. Now I want to give you a test. If you follow us so far, how many samples we needed to the following example. This is a teacher-student setup, but slightly different. Our teacher is a very small size network. The target is a two-layer network with only 2 hidden neurons. And now we use a network with 1000 hidden neurons to fit this 2 hidden neuron network. So each neuron, we have this output weight, input weight, and bias. We have 3 parameters. So the target has 6 parameters. But we don't try this here, okay? And for the model that we are going to train, it has 1,000 neurons, it has 3,000 parameters. Now, makes you clear? We sample the data from this target function and use this data to train this model. The question we want to ask, how many samples if we want to recover this teacher target? We should say 1,000 or 3,000 samples. Okay, now let's review what we have learned. We have shown that if we have this condensation happens, neurons will tend to behave similarly. Neurons in the same layer, they will tend to behave similarly. After training, they get clustered, so the neural network is a small effective network. I will show the answer. So if we have condensation or without condensation, and we use dropout to achieve this, we can see that with condensation, with dropout, this color indicates the generalization, okay? And then this number indicates the number size we use the random sampled to train the neural network. And we have multiple trials to get average. So once we have a number of sample size smaller than 6, this generalization error is quite large. But there's a sharp transition. If we have number of sample size equal or large 6, it suddenly decreases to a very, very small error. But if you don't have condensation, you got to need a lot of samples. Otherwise, you can see the training error is always very large. And this black dash curve is the number of parameters of the target, and it also is an optimistic estimation in our study. So now the question is, we now don't need so many samples that are equal to the parameters to require this target function. And the number of samples somehow equals to the final condensed neural network. So now let's rethink the generalization sample and parameter. For a model with n parameters, how many samples we need? Traditionally, what's the case? It's m, but now we have this optimistic estimation. For example, for this case, once the neurons tends to behave as similar as they can, we actually, after training, have only 6 effective parameters. And it seems we only need to recover these 6 effective parameters. That's enough. So 6 here is the optimistic estimation, seems so. But for a general nonlinear model, how can we get this optimistic case? One of the simplest ways is, suppose we are some god to know everything, and we initialize our parameters very close to some global minimum, very, very close to it. And we train a neural network to this global minimum. So because we are very close to this global minimum, actually we can expand this network around this at this global minimum by theta expansion. This theta prime is our target, our global minimum. And this theta is very close to this theta prime initially. So we can ignore this high order term, only keep this linear form. Once we keep this linear form, this model with respect to this trainable parameter is not nonlinear anymore. It's linear, right? Or we can say it's just a linear combination of this gradient theta f. This is also a function of the input. This dot indicates the input x. So it's just a linear combination. Okay, so we can consider it this way. So each direction indicates a basis of this gradient theta or this tangent. Actually, we consider tangent space is a linear space. And in this linear space, we want to locate this global minimum, this point. How many samples we need? It closely related to the dimension of this linear space, right? The number of samples just need to equal to the dimension of this tangent linear space. Then we can constrain it to a very specific point. So this tangent space is very important if we consider in this way. To give a model, we can get this tangent space by taking the gradient of this function with respect to this parameter. And each parameter will give you a direction. But some direction may overlap or be parallel. So we consider the dimension of their span. This is for any parameter. And for any target function, we can consider the set of parameters that are all global minimum. Meaning we consider this set, this theta. All theta enable to network equals to your target function. And for each theta, it has a tangent space, right? And each tangent space has a rank or dimension. And we take the minimum rank as the rank of your target function in this functional space. This is not easy to understand because this number actually is related to the target function. It also related to your model space. And that is very natural because the generalization should connect to your target function and also connects to your model function. Okay, so there could be a lot of global minimum, and each global minimum should have different complexity. And consider the optimistic estimation, we should consider the most simple one. So we consider the most simple tangent space one. The dimension is the smallest. So if we are able to minimize, to initialize the parameters around this most simple global minimum, we do have chance to use very few samples to recover this target function. So we define this as our optimistic estimation. And for neural network, consider the target function is in the space of your model. If it doesn't, we can use some technique to deal with it. And once the target function is in model space, the model rank or your optimistic estimation will be independent. Note that will be independent with the network width of your model, but only related to your target function. For example, for this target function, you can see the rank is all equals to this m prime here, or d here, but that's not related to this m. That means it's not related to your model parameter number. So you can have many neurons to increase your expressiveness property, but it doesn't harm your optimistic estimation. Okay, so now let's consider in this case, these are three neural networks, and this is the target function. This is exactly the same as the target function, and in this case, we add more connections between neurons. In this case, we duplicate neurons in the hidden layer. So in the traditional estimation, so the parameters here is 12 number, and this 24, and this 24. So we need a number of samples as 12, 24, and 24 to reconstruct this target function. But now, if we consider this optimistic estimation. In this case, it's slightly different because these two neurons, they can be exactly the same. So this number should be 12, but not 24. So that is the case. And how we achieve this? Our previous example shows once we have this condensation, we have chance to achieve this optimistic estimation. So condensation is very important. It's not only give us to achieve this over parameterization generalization, but also give us a hint that how nonlinear model can recover at the optimization or at over parameterization case. We have this optimistic estimation to show that how many number of samples that we need to achieve good generalization. And this condensation enables we can have neural network free expressiveness in ways without hurting our optimistic estimation. And now let's get back to these long-standing problems. Why don't heavily parameterize neural network overfit data? Because our frequency principle and condensation is independent of network size and how many effective number of parameters. We can count the number of parameters of the condensed neural network. And why don't the BP head for poor local minimum? Because of this embedding principle, for the large networks, there exists some critical points that embedded from simple network. And this minimum, they have many descendant direction. So, and they can attract the training trajectory. So the training will go near these simple critical points and then escape. So you will slightly increase, you will gradually increase the complexity until you achieve the global minimum. So it's not easy for the trajectory to be stuck in the local minimum, because in large network, those can attract a trajectory usually have a lot of descent direction. And when should we stop back propagation? For many cases, early stopping can avoid with high frequency noise due to the frequency principle. So we can have conclusion that we have this phase diagram and show that condensation is a very common phenomenon in nonlinear regime. And we have this embedding principle and also help us to have this optimistic estimation for nonlinear model. And this condensation is a very useful trick to achieve this condensation, this optimistic estimation. So condensation is very common, very useful, not only in practical training, but also help us to understand the over-parameterized neural network. And we will stop here. And in next lecture, we will talk about this condensation with large language model and their reasoning ability. For gradient descent, to have this condensation very significantly, we usually need to have very small initialization scale. But once you have very, very small initialization scale, another problem will also emerge. And we have mentioned about this. That is, the loss function during the training process, it will have multiple plateau stage. Definitely, once we have this plateau stage, it will make us wonder if the training will stop or it has encountered a local minimum, and so on. And it also wastes a lot of computation resource. So the training is very, very slow. Now the question is, can we find a way that we have this condensation and we can also have faster training? The answer is yes, it's possible. We can have a dropout technique in the training process. It will facilitate condensation in the whole training process, even for large initialization. Now let's take a look. What is a dropout? So consider a network during the training, and in each training step, we will mask neurons randomly with some probability. So this eta is a random variable, and it has a probability as -1, and if it equals to -1, this element will equals to 0, and this is elements wise product. So the output of this neuron will equals to 0. So this is the original fully connected network, and this is the dropout case. For example, these neurons with this this sign, meaning neurons, its output will be produced with 0. It doesn't have output in this training step. But in another training step, these dropout neurons will be selected randomly again. So now consider in this way, if you want to have some neurons masked, then the output of neurons, the network will definitely be smaller, right? But now, to enable the output of this networks with some masked neurons, you will have a coefficient. For example, the coefficient of the left neurons, the key remainder neurons, is not 1 anymore. It plus some random variable. And the expectation of this eta equals to 0. So consider a very simple case. If you mask half of neurons, then the output of the remainder neurons will be doubled. So the expectation of the output will stay the same. And consider a very extreme case. If after a long-term training, and you want to make this training stable, what should happen? The remainder neurons should be able to compensate the masked neurons, right? And in another extreme case, if all neurons are the same, are exactly the same, then this mask doesn't have any effect anymore, because the remainder neurons can compensate those masked neurons exactly, right? And all neurons are the same, means what? Means condensation happens. So now let's take an example. We initialize the neural network with large initialization, and these training data points, blue data points, are exactly the same for these two cases. And we can see that for large initialization without a dropout, it has a very significant oscillation. But once you have this dropout, it uses a relative flat curve to fit this. And we can also take a look at this feature distribution. Each point here is one neuron, and this x value is orientation from -pi to pi, and the y value is the amplitude. And we can see the initial distribution and the final distribution, they are quite similar. But for dropout, you can see neurons condense in the four direction. It's very different, very different, very clear condensation two-layer network. And for three-layer tinge network, you can similarly observe this condensation happens, and this more flat curve to fit training data. Theoretically, we can understand in this way. We can write out the loss of dropout training. There's some random variable eta, so we can take expectation. After taking expectation, we can get this expectation of loss, not only the mean squared loss part, this is the mean squared loss, and this is an actual regularization part. And this R2, it comes from where? Comes from this discretization of gradient flow. So this R2 is not so important in the study of dropout. So the key thing is, once you use a dropout, you will get another regularization or another term in the loss function in the expectation sense. And this term is irrelevant to the learning rate. So even your learning rate goes to 0, this term still keeps. So this is very different from this stochastic gradient descent regularization. And this term R1, we don't explicitly add to the loss function. So we call it implicit regularization of dropout. Okay, now let's take a look at what's the meaning of this. This is the output of the neuron J in the L-1 layer, because we only use the dropout in the last hidden layer. And this is the output weight. Let me explain what's the meaning of this by a very tall example. So consider we have two neurons. And their output, the summation of their output, should equals to the target output. That is the requirement of mean square error. And this R1 requires the amplitude of this O1, the output of the first neuron and all training data. We put it as a vector. This is the L2 norm of this neuron output on all training samples. This is the network output of the second neuron on all samples. So actually, we require two vectors that they can fit some specific vector. And we also require their amplitude should be equals to the same. Not the same, it should achieve minimum. So in this way, what's the best result? The best result is they should be equal to each other. So in this case, these two vectors summation and these two vectors summation, they are equal to each other, right? But their norm are very different. In this case, this object direction component will add extra value to this this norm. So this will be larger for R1, but this pair will be smaller. So if we have this regularization, we should pick this result. So in this piece, we briefly give you some intuition why dropout can facilitate this condensation, because it drop out some but use the left one to compensate it. And to get a stable training, they should be try to be equal to each other. So this compensation should be easier to be more effective. And in the next, we will talk about the effect of condensation benefits the generalization.